Welcome to the Valve Studio. Our work on this Mectron record player mod continues. We're on the bench. We're going to take some measurements here. We're going to determine the power output. We'll also look at the plate voltage, and we'll see that it matches up with what we found in simulation. But first, I got an early birthday present. I opened it up, and look at this. I got this t-shirt today. That's right. It's Tesla and Edison, the founding members of AC/DC. Now, they ended up splitting because they had artistic differences. And then many years later, Bon and Angus picked up the moniker and took AC/DC to where it is today. All right, before we start out, let me tell you about some problems I had with some of my equipment here. I have a scope here. This is a HP 1222. This is my scope for the Valve Studio. I have other scopes next door that I didn't want to bring in here because of the high voltage. And I didn't want to actually inadvertently blow them out. So this guy is kind of a sacrificial scope, so to speak. And getting set up for today's lab, I found out that this scope has a bad injection of line noise into both channels, A and B. Took it apart and I worked on it for about 3 hours, and I looked at all the power supplies and they looked just rock solid. And I ended up checking a couple capacitors, and I was putting it back together, and I was kind of disgusted because I didn't know what I was going to do at that point. I can't use my scopes from next door. So when I was unplugging it, I noticed something. I'll go ahead and show you that here. And it turns out that it wasn't a problem with the scope at all. It was a problem with the power cord. The ground pin on the power cord wasn't getting brought up to the scope, and that was injecting a lot of noise into that. I looked at the probes and the wires, and I looked at a lot of different things, and it turned out to be that stupid power cord. Replace that. We're back on the bench. Now let's get into taking some measurements. Here's our bench setup for the Mectron record player. Here's the amplifier itself. Over here, I've wired in a switch so I can switch between a speaker and a load on the output transformer, and I have a meter connected up to measure the RMS voltage. Over here, I have an isolation transformer, so I'm running everything off of that because this Mectron amplifier does not have that. It runs directly off the line voltage. I'm running it into my light bulb tester. If I pull the light bulb out, I actually have I can put a fuse in to replace the light bulb, and then that makes this switch actually just a switched outlet. So I have a little bit of protection here with this fuse. Over here I have that voltage divider running up to my Android tablet, and up here it's running the FFT algorithm right now. Right now it's not doing anything because I'm not running any signal into the output. What you're seeing here is the AC coupled. This guy here is the ripple on let's move back here. I think it's having problems focusing on this thing for some reason. Okay, so this is the ripple on the output from the power supply. It's got almost 20 volts of ripple. If you go and calculate out based on our bias point of about 47 milliamps and a capacitor of 30 microfarads, this ripple, if you look at the equation that I is equal to C dV dt, and you rearrange that to give you out the delta V is going to be equal to I over C times delta T. So this delta T, it's halfway rectified, so this is 60 hertz. If you calculate that out, it's about 20 volts here. So this verifies the theoretical calculation for the swing. Now this is quite pronounced here, but when it does go through the output transformer, this voltage here is reduced by the turns ratio, this is 20 volts, and the turns ratio is 33. So that gives us a little bit of ripple out that the speaker sees, which results in a little bit of hum. We can fix this by increasing the power supply capacitor. But we won't do that today. We'll live with what we got because this is the original amplifier design that we've been working with the whole time. This setup here, I don't have any signal applied. So this, you're seeing the DC signal here. And I'm going to turn on my signal generator. And you'll be able to see over here, we actually are imposing, what do we have over here? Well, this guy's at 1 kilohertz. So you can see the 1 kilohertz is superimposed on that ripple. And you're going to get to see that that ripple is actually going to cause us a lot of problems. So what I ended up doing was I added an additional high-pass filter capacitor. So when we move our scope probe on the other side of that filter capacitor, we can get rid of a little bit of that ripple. We still have a little bit of it here, but we can kind of live with this amount right here. I really need a notch filter to knock that out, but we're going to live with what we got. Over here, you're going to see that here's the FFT. We're at 1 kilohertz here. I know you can't really read this, but we're about 76 dB on the fundamental. Our second's down to about 46 dB down, and our third is probably about 40 dB down. So this is a fairly good signal. 40 dB down was going to be, well, let me see, 20 dB down is 1%. So this is 0.01% distortion right here. And our output voltage is 0.34, so that works out to be, our power output right now is 0.34 squared divided by 4. We're down about 50 milliwatts. So our power output's really low right here, but you can see that things are working. This upper trace is actually the gate voltage going into the 50L6, and this is at 1 volt per division. So we're driving it with about plus or minus 1 volt. I'll go ahead and turn it up here. Okay, so when we drive it with plus or minus 1 volt, we are still looking pretty good on our distortion. We're 40 dB down, so we're at 0.01% distortion, and our voltage went up to 0.43 volts RMS. So that is going to be, our power output now is about 50 milliwatts. It's if I had the speaker on, it'd be pretty loud in here. Okay, let's go ahead and raise this up so that we get some visible distortion over here. And I'm going to need to switch this now. I'm going to switch this up to 50 volts per division. And I need to switch this one as well. All right, so what you're seeing now is a little bit of visible distortion on the upper side. All right, now this kind of looks odd here because we have that filter capacitor to knock out the 60 hertz. I'm going to take that off. I'm going to put my scope probe directly on the plate of the 50L6, which is this bottom trace here. All right, so that's kind of the output that's actually getting fed into the transformer, which is really what we expect to see. When this voltage goes high, this is approaching a gate voltage of 0. I mean a grid voltage of 0. So we're nearing saturation. So our current change is not as we don't see a lot of current change. Remember those 3 points that are smashed together on the plate characteristic? So what we're seeing down here is a squaring off of the waveform going the plate waveform. So we're really close to what we predicted. And if you look over here now, we have a lot of harmonics going on. We have a second that's probably, let me see, we're up to Actually, what's going on is we're overdriving the input to this, so I need to turn down the amplitude into the spectrum analyzer because we were clipping the input. See, if I overdrive the input, we actually run a square wave into that. So you have to be pretty careful with spectrum analyzers that you don't overdrive the input, but this is about where we really should be. So we're about 72 now. Our third is down at 50. So now we're about 10% distortion right here because we have a second, a third, a fourth, and a fifth now. And this is audibly really distorted. Let me turn everything off and we'll see what this really sounds like when it gets up to this level. So we're going to turn this off. Let me see, I'm going to click this guy off here. It's going to get really loud in here, but I'm going to go ahead and run it when it's really clean, and then we'll go ahead and turn it on. And we're going to hear a lot of just, well, I don't know what's going to happen. Let's see. All right, so down here you can kind of see that what our harmonic content is. All right, that's just painful. Let's not do that again. Just click this speaker back over here. Turn this thing off. All right, let's back on the load resistor now. Let's get back to business. So I'm back on the load resistor, and we'll go ahead and get this turned back up again. We'll go ahead and look at a couple other things while we're here. I'm at 50 volts per division here, so if you can see we have our 0 point is going to be on that line right there. We're AC coupled, so we have our plate output swing is about 100 volts down, and then about 100 volts back up again. So if I'm going to turn this up, and I'm going to go to DC coupled here, so we can kind of see what's going on. And I'm going to move the DC reference down to the bottom of the graph. So now, in order to let me see if that's good. All right, so I'm back on 50 volts. So here is this is the operating point voltage, which is 50 volts, 100 volts, about 125 or so is about what we anticipate it to be. If we bring this back, turn this back up again. So right down here, this starts to clip down here. That area right there is going to be about 25 volts, which is really close to what our load line shows. Because this is where those 3 points, this is nearing saturation, so we don't have a lot of current flow, and that's why this is clipped down here. This up here swings. It's not quite linear. I mean, it's not quite a sine wave either, because we're on a different area of the transfer curve. Our power output now is well, let's get this down to right about where we start to hear some distortion. If you look over here, we're about 30 dB down. So right around in here is where it becomes audible. Our voltage is our voltage on a load resistor is 2 volts. which works out to be about a watt. So we get about a watt out when the single-ended amplifier runs in 50L6 at roughly about 5% distortion, I would suspect. Well, let's wrap it up here for today. We're not going to measure the frequency response because we didn't do any theoretical analysis of that before we got started. And it doesn't really matter because the half-wave rectifier adds a little bit of trouble to measure the low end on this amplifier. And on the high end, it's got that kind of funky tone control. And it's not really that important because this is a little stupid little practice amp. So we'll end here. And we really do want to measure frequency responsive amplifiers, but we'll do it when we actually do a design. We'll get on the bench and we'll show you some techniques to measure that. Okay, well, thanks for watching today. This is the Valve Studio.